All right, let's go ahead and get started. I do want to welcome you to Unit 2. This is Atomic Theory. The introductory unit now is behind us, as well as the Unit 1 on the nature of matter. We're going to be talking in this unit about the fundamental building block of all of matter, what we will call the atom. All right? And in particular, we're going to want to know the historical events which led us to our modern concept of the atom. We have some ideas today about what the atom is, because we can't see it, obviously. We have to conceptualize it in our minds. And so we're going to be looking through some specific experiments that were done to help us to understand the nature of the atom. I do want to tell you that I'm going to be moving fairly quickly through this unit because of the fact that I think it's factual and historical, certainly important, but nothing that requires a great deal of practice or technical information that needs to be given to you. So I'm going to be moving fairly briskly so that we can spend more time in Unit 3. So here we go. Follow me. It says matter is everything in the universe which has mass and occupies space. So that's the criterion, right? If you take a piece of matter, let's say it's silver, and you cut it up again and again and again many times, eventually you get to the point you can't cut it anymore. It doesn't matter how refined the instrument that you use to cut. The fact of the matter is you're eventually going to get to the point where you just can't make a smaller particle. The tiniest bit of matter is known as the atom. All right, so the atom is the basic building block of all matter. Atoms then are the basic building blocks of everything around us. The story of how we came to know this is that the atom is the basic unit of nature is interesting, and one that we're going to begin our study of chemistry with. So here it goes. So I want to start with in ancient Greece, right? This is about 400 BC. And in ancient Greece, there lived a man named Democritus, who believed everything around him was made of very, very small particles. He called these particles atomos. So atomos means building block or the beginning. Unfortunately, the scientific method, a system for methodically asking questions until you arrive at the right answer, had not yet been developed. So the idea of a fundamental particle making up all the material in the world was forgotten until much later, the early 17th century. So this is a picture here then of Democritus, or not a picture, but it looks like what Democritus might have looked like in that day. And this was his concept of the atom, fairly straightforward. In 400 BC, he simply thought that the atom was a sphere. That was it, right? So in 1803, so many centuries passed before John Dalton, an English scientist, was performing experiments with various materials in his laboratory. Now, the results suggested that Democritus was correct. He was right. The universe was made of atoms, right? Now, and by the way, Democritus and Dalton didn't completely agree. For example, Democritus believed that atoms, or the basic building blocks of, say, water, were smooth and clear, like water was, and that the building blocks that made up of, let's say, iron were hard because iron was hard and so forth. It turns out to be completely incorrect, but nonetheless, that was in 400 BC, our initial understanding of the atom. But then again, we get to 1803, John Dalton, and he comes up with a series of experiments, some very painstaking experiments in which he's measuring the amount of matter that's present in these experiments. And here's what he comes up with. This is Dalton's atomic theory. Number one, all matter is made up of tiny particles called atoms. So he calls them atoms, right? It says, number two, all atoms of a given element are alike, but different atoms from any other element, right? So Dalton believed that all of the atoms of, for example, silver were alike, but the atoms of gold and silver were quite different, okay? So that was his second postulate. Third postulate, compounds are formed when atoms of different elements combine in fixed proportions, right? So for example, he determined that water is always H2O. It's never HO or H3O. Carbon dioxide was always CO2. These proportions, Dalton said, were fixed, right? Number four, a chemical reaction involves a rearrangement of atoms, not a change in the atoms themselves. So the atoms themselves remain what they were before the chemical reaction, but there was a rearrangement of atoms in the chemical reaction. So this was Dalton's atomic theory from 1803. Now let's fast forward. All the matter in the universe was indeed composed of tiny particles, which Dalton calls again atoms. Now, for 30 years, the atom was thought to be the smallest particle in the universe. But in 1835, and by the way, you don't have to remember dates. You simply have to remember the people that were involved and what their contribution was. So 1835 is really not important. But what is important was the individual, J.J. Thomson. J.J. Thomson conducted a very important experiment using a special glass tube known as a cathode ray tube. The cathode ray tube, or this tube, contained what Thomson believed to be a beam of light known as a cathode ray. But through a series of experiments, Thomson found that the cathode ray was not a light beam at all. It was a beam of tiny particles, matter, in other words. These particles were much smaller than the atom. Let me read that again. These particles were much smaller than the atom. Now remember, it was previously thought that the atom was the smallest particle in nature. So this meant that atoms were not the smallest particles after all. J.J. Thomson had discovered a particle, a small fraction of the size of the atom. That was the electron. So for the first time, we know about particles that are smaller than the atom. They're called electrons. Further testing revealed that the electron was negatively charged. Let's take a look at those studies. So here it is. This is the cathode ray tube, right? This is a model of the cathode ray tube. So what would happen is that from this end, right here, that these cathode rays would be shot across in a line from left to right, as shown on our notes, from left to right. But an interesting thing would happen when he placed a plate here and here. Now the top plate was positively charged. The bottom plate was negatively charged. And what happened was that as the cathode rays were moved from one side to the other, from say left to right, what happened was that these cathode rays would deflect, right? What did that mean? Well, they always deflected in the direction of the positive plate. That meant that these particles, these electrons, must be negatively charged, because J.J. Thomson knew that the particles would be attracted to a positive plate if they were negatively charged. But the opposite would be true if they were deflected towards the negative plate. And so a model of the atom emerged of tiny electrons embedded in the atom like plums in a plum pudding. Very important that we remember that phrase, like plums in a plum pudding. So let's take a look at that model. This is it. So it was no longer believed then, after J.J. Thomson's experiment, the atom was simply a sphere. But now we believe it to be a sphere with particles, negatively charged, very small particles called electrons, embedded throughout, like plums in a plum pudding. And by the way, I've never had plum pudding. I know of individuals who've had it, and they say that it is what it sounds like. So it's pudding with plums embedded throughout, and so the electrons are like the plums in a plum pudding. All right, so that's that. Let's move on now. It says the plum pudding model stood for a number of years until Ernest Rutherford, another important name, performed another important experiment. In this famous experiment, which has come to be known as the gold foil experiment, Rutherford fired tiny particles known as alpha particles, or helium nuclei, at a thin sheet of gold foil. All right? Rutherford assumed that since the electrons in the gold atom were so small that the alpha particles would easily pass through the gold foil, which is made of gold atoms. What he found instead astounded him. Most of the time, the alpha particles would pass straight through, but every once in a while, an alpha particle would be deflected at a sharp angle. This finding implied that at the core of the atom was a dense, positively charged center. Rutherford had discovered another particle within and smaller than the atom. This particle was known as the proton. So Rutherford's model contained the electrons embedded throughout the atom, but with a dense, positively charged proton containing nucleus in the center. A clear picture of what the atom really looked like was beginning to emerge. So this was the apparatus. This was the gold foil experiment that Rutherford used. What he did was he shot alpha particles, which are, by the way, radioactive. That's why we need a lead block shield. So he shot alpha particles in a beam right through a gold foil. So he placed a gold foil here, a piece of gold foil here. Now he expected that the alpha particles, which are fairly large and dense, are going to move straight through the gold foil because of the fact that, well, there's really nothing to stop them. The tiny electrons that are embedded throughout the atoms of the gold are certainly not going to stop those big, fast-moving alpha particles. So he expected the alpha particles to move straight through, and indeed they did most of the time. But every once in a while, there would be a deflection. So every once in a while, as the alpha particles were shot through, right, there would be a deflection in one direction or the other. So maybe and sometimes even a sharp deflection, like this way or this way. How is this possible? What was causing this to happen? By the way, on the outside was a zinc sulfide screen that these alpha particles could be detected. So how is it possible then, if the atom was only composed of electrons embedded throughout the atom like plums in a plum pudding, that there was this tremendous deflection, right? There was a tremendous deflection. So what Rutherford surmised was that in the center of the atom, in addition to the electrons embedded throughout, right, there must have been a dense core. So the electrons were embedded throughout the atom, but they were certainly not going to stop an alpha particle. But in the center of the atom was a dense core, and he later discovered that within that dense core was a subatomic particle, a particle smaller than the atom, called a proton, right? Now, around 1934, James Chadwick, another important name, did a series of experiments in which he discovered a particle in the nucleus of the atom. It was about the same size as a proton, but unlike the proton, it carried no charge. It was a neutral particle, and it was named the neutron. So within a fairly short amount of time, we have the discovery of the electron, the proton, and the neutron within the nucleus. So the electrons throughout the atom, but the proton and the neutrons within the central part of the atom in an area called the nucleus. 2 years later, Robert Millikan performed an experiment known as the oil drop experiment. In this process, in this experiment, Millikan calculated the charge on single electrons. Folks, I'm going to go ahead and put this in the notes, but I do want to tell you this. I only ask that you remember that Robert Millikan is responsible for measuring the size of the electron. This is called the oil drop experiment. It's fairly complicated, so I'm not going to require that you know the details of the experiment. Simply that Robert Millikan was responsible for discovering the size of the electron. Okay? Folks, we're going to end this here. We're going to look at the next important discovery in our next video. This will come in 1942 through an important scientist named Niels Bohr. I'll see you in the next one. Thanks. Bye-bye.